Hello and welcome to our geodetic tutorial. My name is Janine Hilden. I'm an application engineer at Math2Market, and in the following video I will show you how you can charge a battery considering the concentration dependent parameters of an active material. In Geodetic 2024, this is already possible by using the corresponding expert setting. First, we need a cathode to be loaded. I have prepared one with our Electrode Geo app. Here the NMC particles are visualized in light gray and the binder in red. The next step is now to set up the concentration dependent parameters for the NMC 333. How do we do that? The expert setting expects a text file containing a table with two columns. The first should provide the removable lithium concentration values in mole per cubic meter. The second should consist of the corresponding concentration-dependent diffusivities in square meters per second or the electronic conductivities in Siemens per meter. You can request the text files containing concentration-dependent parameters for many of the materials in our database. Just write to support@math2market.de. Look in the video description for instructions. We also provide a documentation on how to prepare such text files for your own materials. Let's have a look at the text files. In the left column, we see that the removable lithium concentration values range from 0 at 0% material SOC to the maximum removable lithium concentration at 100% material SOC. For NMC 333 shipped with Geodict, the maximum removable lithium concentration is about 35,500 mol per cubic meter. The corresponding interpolated lithium diffusivity values range from 1.4 E-14 to 7.6 E-14 square meters per second. Additionally, we have here a similar file where you can observe the removable lithium concentration in the left column and the dependent electrical conductivity in the right column. For my convenience, I copied the two needed text files to the project folder I use for this tutorial. Before we start using the concentration-dependent parameters, we will perform a simulation with non-concentration-dependent values as a comparison. For this, open the BatteryDict module by selecting Predict, BatteryDict. Then here, select Electrode and here, Charge Electrode. Click Edit. First, we change the result file name. We will start with a fast simulation without using concentration-dependent parameters and using the homogenized model. In the Solver tab, select Homogenized Simulation for simulation type and click OK and charge. It will run quite fast, and then the result file pops up in the result viewer. Have a look at the created battery cell by moving to the Data Visualization tab and clicking Load Cell GDT. Here we can see that our NMC 333 is the cathode active material 1. Charge Electrode creates a half cell with the investigated electrode as a cathode. Hence, the first active material in the electrode is always cathode active material 1. If you simulate charging on the battery with anode and cathode, the anode active materials will be called anode active material. Now, load the cathode structure again. And then, with the knowledge about the material naming conventions, go to Settings and then Edit Expert Settings. Click Add Row and select BatteryDict. Click OK and then select Charge Electrode. If I would simulate a whole battery with the Charge Battery command, I would of course select Charge Battery. Then, here I have to know which active material I want to edit and which type of data I want to add. We select Cathode Act Mat1 lithium diffusivity file. Here I need to enter the name of the text file containing the needed concentration-dependent values. So just copy the name and paste it here. I only need the name because it's in the project folder. You could also enter the complete file path or the path relative to the project folder. Now click OK and open the charge electrode parameters again. Change the result file name and charge again. Now the concentration-dependent diffusivity values are used for the NMC. How can we know from the BetterPredict result that the expert setting was used? Just go to the Metadata tab and unfold expert settings down here. Here the expert setting is shown. As we now have two charging simulation results, we can compare them to each other. Keep Ctrl pressed while selecting the no-count step file. To compare the plots, click Combine Results and enter Compare Homogenized Simulation. And click OK. In the Plots tab, we can see that the cell potentials differ. Have a look at the overpotentials. Here we can see that the diffusivity in the cathode is different. Right-click in the plot, uncheck Toggle All, and select the two diffusive cathode plots. The curve with the higher overpotential belongs to the simulation without concentration-dependent diffusivity, and the other curve belongs to the concentration-dependent diffusivity simulation. Considering the concentration dependence, at lower lithium concentrations we have a lower diffusivity. This is why we have a lower overpotential for the simulation, also leading to a different charging curve. Of course, we also want to see what happens if we additionally consider concentration-dependent electrical conductivities. For this, open the expert settings again and add a row, similar to before. But in the last step, select the key cathode ActMat1 electronic conductivity file and copy the name of the corresponding text file. Please note that this expert setting does not work with the homogenized model, but only with the fully resolved model using the BEST microsolver. The concentration-dependent diffusivity works for both the fully resolved and the homogenized simulation. Again, change the result file name. Then, under the Solver tab, change to the fully resolved simulation and choose the BEST microsolver, because otherwise the concentration-dependent conductivity cannot be used. To simulate very fast charging, I also changed the charge rate to 2. And click OK and charge. On my laptop with 8 cores, the simulation took about half an hour. I have already prepared a result file for a simulation with the same settings without using the concentration-dependent parameters, so I can just combine the results again and view the differences. The curve for the concentration-dependent conductivity simulation shows a lower cell potential than without using the concentration-dependent parameters. Also, the overpotentials are lower for the concentration-dependent parameters. If we have a look at the electrical resistivity, we can see that it is higher for the concentration-dependent parameters, leading to a lower overpotential. This is because the electrical conductivity in the NMC is considered to be lower for a high lithiation. Because we have a good conductive network in the carbon binder domain of the electrode, the overpotentials due to the electronic resistivity of the cathode are small. Thus, the effect on the battery in this example is not so prominent as the effect of the concentration-dependent diffusivity. This is the end of this video tutorial. I showed you how to simulate charging considering concentration-dependent parameters for the active material. If you found this tutorial helpful, please check out our Math the Market channel for more geodetic videos. Goodbye!